Okay, so welcome everyone to the non-commutative geometry seminar. So it's a pleasure to have Jens Kool speaking from Syddansk Universiteit. So onze exterior products. Yeah, apologize to my pronunciations, of course, but exterior products of compact quantum metric spaces.
Yes, thanks a lot, Walter, and thanks to all of the organizers of this NCG seminar for inviting me. It's a great pleasure to talk on this occasion. And I also apologize to those of you who have heard this talk already, because I gave it at an NCG learning seminar in Copenhagen also. But I think it was not everyone who was present there, so it should be okay. So what I'm going to talk about today is compact quantum metric spaces. And this was a theory that was initiated by Riefel back in the 90s. And I think primarily building on the observation due to Kohn that if you have a compact spin manifold, then you can recover the metric on this compact spin manifold exactly from the interaction between the Dirac operator and the C-star algebra of continuous functions on this compact spin manifold. Now, if you are in a more general context, so if you're looking at unital spectral triple, which we have learned over the past 30 years to think of as a non-commutative geometric space, then you always have an interesting seminorm on the unital C-star algebra in question. And this seminorm amounts to taking the norm of the derivative of an element. Okay, once you have a seminorm on a unital C-star algebra, then you can construct a metric on the state space of this unital C-star algebra. And this is called the Monge-Kantorowicz metric on this state space. If it then happens that this metric actually metrizes the weak star topology, then you have what is called a compact quantum metric space in the sense of Riefel. So if the seminorm comes from a unital spectral triple, then you say that you have a compact spectral metric space, which is then a special case of a compact quantum metric space. If you have two unital spectral triples, then you can take the exterior product. So you can take like the tensor product of two unital spectral triples. And if you do this construction in the context of compact spin manifolds, then you recover exactly the Dirac operator on the Cartesian product of these two compact spin manifolds. In particular, from this tensor product of unital spectral triples, you get exactly the correct metric on the Cartesian product of the underlying compact Riemannian manifolds. So it becomes a relevant question to ask whether, if I have two spectral metric spaces, so two unital spectral triples that give rise to compact quantum metric spaces, is it then true that their exterior product is again a compact spectral metric space? And this is the question I'm going to talk about today. But before I can go that far, I will present some preliminaries on compact quantum metric spaces. And also I will present a new characterization of what it means to be a compact quantum metric space, this time in terms of finite dimensional approximations. So that's more or less the program for this talk. Let me see whether I can. Yes, okay, here we go. Yes, so a convenient context for talking about compact quantum metric spaces is context of operator systems. So just to remind you, this is a concrete operator system there's a closed unital subspace of the bounded operators on some Hilbert space, and it's also closed under the adjoint operation. So if I have an operator X inside that operator system, then the adjoint also belongs to this operator system. It's a closed unital subspace, which is closed under the adjoint. Okay, once you have an operator system, you have a state space. So you can talk about states on an operator system. Those are the linear positive functionals on this operator system that maps the unit to the unit. So positivity in the operator system is inherited from the bounded operators in the Hilbert space. So everything makes sense here. You can look at the state space. This is a set of all states on this operator system, and this is a compact Hausdorff space when you equip it with the weak star topology, so pointwise convergence of states. Okay, so we are interested in metrics on the state space of an operator system. And these metrics, they're going to come from seminorms that are defined on the operator system. So I'm going to work with a particular kind of seminorms. They're called Lipschitz seminorms. So they satisfy some extra properties besides just being a seminorm. So one thing which is a bit peculiar is that my seminorm can take the value infinity, but otherwise it satisfies all the typical requirements for being a seminorm. And then it's Lipschitz. It means that, first of all, it cannot see the difference between an operator and its adjoint. And moreover, it has to be densely defined. So the domain of this seminorm consists of all operators where the seminorm is finite. And this has to be norm dense inside my operator system. So dense with respect to the operator norm. Okay, third condition is that my Lipschitz seminorm, it has to be lower semi-continuous. This I can rephrase as follows. Whenever I have a radius r, I can look at the Lipschitz ball with radius r. So it consists of all operators where the Lipschitz seminorm is less than or equal to r. And this has to be closed in operator norm. So that's equivalent to requiring the seminorm to being lower semi-continuous. And last, the Lipschitz seminorm has to vanish on the unit in my operator system. So an operator system is unital. It's more common to say that a Lipschitz seminorm has to vanish exactly on the scalar multiples of the unit. But for the purposes of this talk, I'm using this slightly more flexible definition that the kernel should just contain all scalar multiples of the unit. Okay, and good examples of Lipschitz seminorms, especially if you're doing noncommutative geometry, they come here. So if you just have an unbounded self-adjoint operator acting on a Hilbert space, you can define a seminorm on all of the bounded operators on the Hilbert space, but it can take value infinity. How do you do that? If you apply it to an operator, it has to give you a positive number or infinity. I find that number, I take the supremum over all elements in the domain such that the Hilbert space norm is less than or equal to 1. And then I take supremum of absolute value of difference of two inner products. I look at d psi t eta minus t adjoint psi inner product with d eta. So what this really wants to be, is just, it really wants to be the norm of the closure of the commutator between d and t. This is what this really wants to be. But this quantity for a general bounded operator need not make sense at all. It need not even be a densely defined operator. Yeah. But the following holds that that an operator belongs to the domain of the seminorm, so it has finite value if and only if the operator preserves the domain of D, and the closure of the commutator between D and T is bounded. So that's an equivalent condition. And in this case, you actually have that the seminorm applied to T is exactly the norm of this closure here. This you can check. Okay, then I need to define an operator system coming from my unbounded self-adjoint operator here. I just look at the domain of this seminorm and I take the norm closure of this domain. And this is an operator system, and it can be proved that the seminorm, when restricted to this operator system, is a Lipschitz seminorm. This is a very general construction of Lipschitz seminorms. Okay. So once you have such a Lipschitz seminorm, you can define a metric on the state space of your operator system. It's called the Noncommutative metric. So I have to explain what it does to two states. Again, it can take the value infinity, but otherwise it satisfies all the usual properties of being a metric. So the distance between two states is supremum. I look at all elements in the Lipschitz unit ball. So all operators where the Lipschitz norm is less than or equal to 1. And then I look at the difference of absolute value of the two states applied to my operator. Take the supremum. So that's the distance between these two states. And then you say that the pair consisting of this operator system and the Lipschitz seminorm, this is a compact quantum metric space in the sense of Riefel. Once this metric, the Noncommutative metric, metrizes the weak star topology on the state space. Okay, so super good question is, suppose that you now give me an operator system and a Lipschitz seminorm. How do I verify that I have a compact quantum metric space? And I mean, it sounds like I would need to understand this operator system. I would need to understand the state space and this metric. Fortunately, there's an equivalent characterization of what it means to be a compact quantum metric space, which is due to Riefel. It comes here. And I think so. This theorem here was also proved by Branka Pavlovich around the same time. But it seems like she got the problem from Riefel, but I don't know the story that well. Maybe someone else knows it. Okay, so here are two ways of saying that I have a compact quantum metric space. The first one is the obvious way, and the other one is the interesting one. The second one is that, so instead of checking directly that I have a compact quantum metric space, I can instead check that a certain subset of the quotient space is relatively compact with respect to the quotient norm. So this subset has compact closure. The subset I'm looking at is the image of the Lipschitz unit ball under the quotient map. So instead of verifying directly that I have a compact quantum metric space, I can check instead that a certain subset is relatively compact. And what you usually do in practice is that you check the second condition. This is the only one you can check in practice. All right. I promised that I would give you a new characterization of what it means to be a compact quantum metric space in terms of finite dimensional approximations. So I will now explain which kind of finite dimensional approximations I'm going to use. Okay, so you start out with two constants, epsilon and c. And then you look at what is called an epsilon, c approximation of the pair here consisting of your operator system and your Lipschitz seminorm. So this is going to be a pair iota, phi of two unital linear maps taking values inside some auxiliary operator system set. Okay, these two maps, they have to satisfy some conditions. The first one are some inequalities. The first two inequalities say that iota here is bounded, that the inverse is well defined, and that the inverse is also bounded as an operator. And the operator norm of both iota and the inverse of iota are dominated by my constant c. The second condition says that phi is also bounded and the operator norm is dominated by my constant c. Okay. Here comes the finite dimensionality. The image of phi has to be a finite dimensional subspace of the set, of the operator system set. Okay, third condition, this is the approximation property. It says that iota and phi are close to one another when compared with the Lipschitz seminorm. So iota of x minus phi of x, this distance is small. Compared to the Lipschitz seminorm, it's dominated by epsilon times the Lipschitz seminorm. So here's the other constant epsilon appearing. And I think it's very good to see an example of such an approximation. So I will try to share my whiteboard and then give you an example, if I can. Let's see. I think, can you see the whiteboard now? Yes, okay. So let's just look at the case where you have a compact metric space. Then I can define a Lipschitz seminorm on the continuous functions, C star of continuous functions on this compact metric space. It's just going to pick up the Lipschitz constant once this is defined, otherwise it's equal to infinity. So LD of f, it's supremum over difference of f of x minus f of y divided by distance between x and y. And then of course I only look at x and y that are different. Otherwise I cannot divide by the distance. Okay, this is my Lipschitz seminorm. Now I'm going to consider some epsilon strictly greater than 0. And then we define an epsilon comma 1 approximation of this, of the continuous functions on M equipped with this Lipschitz seminorm. How do you define it? I just choose a partition of unity. Just a partition of unity, phi j, finite partition of unity, such that the support of phi j is contained inside a ball with radius epsilon and some center xj. This is ball radius epsilon and center xj. This I can always choose, have a compact metric space. And then I put iota equal to the identity operator, and phi, from my definition, I have to explain what it does to a function f. Well, I just do the sum of my partition of unity, phi j, times the value of f at the center of the ball here, xj. And then this pair, iota comma phi, is my epsilon comma 1 approximation. So that's what it looks like in the commutative case. All right, so let's go back. So this is a very good example of one of these finite dimensional approximations. So you can see here the image of phi is finite dimensional, it's spanned by these phi j, for example. So let me go back to the talk if I can. Yes. All right, now we are ready for this new characterization of what it means to be a compact quantum metric space in terms of these finite dimensional approximations. Okay, so here are two equivalent conditions. The first one is, again, the trivial one. You have a compact quantum metric space. The interesting one is part 2. It says that I can find a global constant C strictly greater than 0, such that the following holds. So there are two conditions. The first one is not surprising if you know compact quantum metric spaces. It also appears in the work of Riefel. The first condition here is equivalent to saying that the state space equipped with the most controllerage metric has finite diameter. So that's equivalent to the first condition. It says that the quotient norm is dominated by the Lipschitz seminorm up to this constant C, up to some constant, okay? But here C is globally fixed. The second condition is the new one. It says that I can find an epsilon comma C, such a finite dimensional approximation of my operator system and Lipschitz seminorm. I can do that for all epsilon strictly greater than 0. So it's important here that the C is not allowed to depend on the epsilon. I have to be able to use the same constant C for all epsilon strictly greater than 0. All right, so this you can actually check now using condition 2, and the example I just gave you of an epsilon comma 1 approximation in the case of compact metric spaces to check that continuous functions on a compact metric space is indeed a compact quantum metric space, if you want to. But now I'm going to the second leg of this talk, which is about unital spectral triples and their products. So here are some reminders for a lot of you. Okay, so an even unital spectral triple, this is a triple where A is a unital C star subalgebra of the bounded operators acting on the Hilbert space, which is the second ingredient, separable Hilbert space. I also want my Hilbert space to be Z-mod 2Z graded. I want to look at even unital spectral triples. So H splits up as a direct sum, H plus direct sum with H minus, and all operators in A have to be even. So they are diagonal with respect to this direct sum decomposition. Then I have an odd unbounded self-adjoint operator acting on this Hilbert space. And then there are conditions. The first condition I have rephrased slightly because of the context of this talk. It says that the intersection between the unital C star algebra and the domain of the Lipschitz seminorm coming from this unbounded self-adjoint operator, that this intersection has to be norm dense inside A. So this intersection here is exactly the usual Lipschitz algebra. It's norm dense inside A. And then second condition is that the resolvent of D is compact. Then you say that you have a spectral metric space or compact spectral metric space. I think this terminology is due to Belisar, Marcoli, and Raihani. You say you have a compact spectral metric space when your even unital spectral triple gives rise to a compact quantum metric space, meaning that the unital C star algebra equipped with this Lipschitz seminorm is a compact quantum metric space. Then you have a compact spectral metric space. If you have two of these even unital spectral triples, you can take their product. So it comes here. If you have two even unital spectral triples, you can construct their exterior product. So this is again a unital spectral triple, very explicit. The correct C star algebra is the minimal tensor product of A and B. It acts on the Hilbert space tensor product of H and G. And then you have this unbounded product operator, D times E. So this is an odd unbounded self-adjoint operator acting on this Hilbert space tensor product. you define it as the closure of an unbounded symmetric operator, namely this tensor sum, d tensor 1 plus gamma tensor e, which is a priori just defined on the algebraic tensor product of the two domains. And it takes values inside the Hilbert space tensor product. So you take the closure of this unbounded symmetric operator, you get the unbounded product operator here. And this is the exterior product of even unital spectral triples. It's again an even unital spectral triple. It's not entirely trivial to prove. I think it's due to Bas and Julk, but it could have been noticed before their paper in the beginning of the 80s. Also, gamma here appearing is the grading operator on the first of the two Hilbert spaces. All right. So now comes the main question for this talk. So suppose I have two compact spectral metric spaces. Then I can form their exterior product because they are both even unital spectral triples. Is it then true that this exterior product is again a spectral metric space? So can I metrize the weak star topology on the state space of this minimal tensor product using this unbounded product operator? So that's the main question for this talk. And yeah, I spent quite a while thinking about this problem, and I couldn't really solve it. And I thought perhaps, yeah, I realized that I didn't really understand what happens just if you take, if you just tensorize with n-by-n matrices. So this is quite interesting to consider. Let me see. So because of the following observation, if I start from a unital spectral triple, AHD, and then I tensorize with n-by-n matrices. So I then get n-by-n matrices with entries in A, acting on n copies of the Hilbert space. And here I have n copies of my unbounded self-adjoint operator acting diagonal. So if this is an even unital spectral triple, this is again an even unital spectral triple. But when n is strictly greater than 1, this is never a spectral metric space. It can never happen. Disappointing, but so when you just tensorize with n-by-n matrices, even if you start with a spectral metric space, you will never get a spectral metric space. And why not? It's because if you have a spectral metric space, you actually know something about the kernel of your seminorm. You know that this kernel has to agree exactly with the scalars. But when you have tensorized with n-by-n matrices in this fashion here, the kernel of the seminorm coming from this diagonal operator will at least contain n-by-n matrices with scalar entries, which is too big. So it's never going to be a spectral metric space.
Sorry, Jens, can I ask a question?
Yeah, sure. Who's speaking?
Yeah, but I mean, here the problem seems to be that one of the two spectral triple is not a spectral metric space. You take a trivial Dirac operator on matrices, and so that is not a spectral metric space.
Sure.
So you are cheating a little bit.
Slightly.
Yeah.
I am cheating slightly, but it's just to emphasize some structural property of this theory that one has to take seriously. Yeah, it's true. If I just look at n-by-n matrices with complex entries and the trivial Dirac operator, it's not a spectral metric space either, because the kernel is again too big. But it emphasizes some structural problem that I want to deal with, because yeah, so my solution to this problem I have is to try to incorporate this stabilization operation into the definition of a compact quantum metric space. So this means that I would like to pass to a completely bounded setting. when I deal with compact quantum metric spaces. And if you happen to know some operator space theory, you will know that if you look at operator spaces, you have to not only consider what happens on the operator space itself, but you always have to keep track on what happens on n-by-n matrices with entries in the operator space. So the first thing I will do now is to lift my definition of a Lipschitz seminorm to an operator space context. And this comes here. So this is going to be plagiarism from operator space theory, what I'm doing now. So here's an operator seminorm. So once you have an operator system, now I can define what is an operator seminorm on this operator system. Well, it's not just a seminorm on the operator system itself, it's a collection of seminorm. I have one in each degree, one for all n-by-n matrices with entries in this operator system. Again, it can take the value infinity. Okay, then there are two conditions that are very familiar from operator space theory, from the definition of an operator space. If I apply my operator seminorm to a product of an element X, which is an n-by-n matrix with entries in my operator space, and then from the left and from the right, I have two n-by-n matrices with scalar entries. Then this seminorm has to be dominated by a product, namely the operator norm of V times the Lipschitz seminorm of the seminorm of X times the operator norm of W. Okay, first condition. Second condition, if I have a direct sum of two matrices with entries in my operator system and I apply my seminorm, then I want to be able to compute this as a max of the seminorm applied to each of the two factors. So that's an operator seminorm. I will say that it's Lipschitz. This operator seminorm is Lipschitz once the seminorm in each degree is a Lipschitz seminorm. So all of these seminorms appearing have to be Lipschitz seminorms, and I have a Lipschitz operator seminorm. I should emphasize that n-by-n matrices with entries in an operator system is again an operator system, because I can represent them as bounded operators on the n-fold direct sum of H with itself. So this is again an operator system. So this definition makes sense. Okay, examples of Lipschitz operator seminorms. Let's see, where are they? Going back. So again, if I have an unbounded self-adjoint operator acting on my Hilbert space, I can now define a seminorm in each degree. So on n-by-n matrices with entries that are bounded operators on H. How do I do that? Well, I just look at the n-fold direct sum of D with itself. This is again an unbounded self-adjoint operator. So using my previous construction of a seminorm, I can just repeat that for this unbounded self-adjoint operator. I get a seminorm on the bounded operators on the n-fold direct sum of H with itself, which identifies with these n-by-n matrices. Okay, that's my seminorm in degree n. I want to have a Lipschitz operator seminorm, so I have to look at a slightly smaller operator system here. I have to again look at the operator norm closure of the domain of this seminorm in degree 1. This is my operator system. And then you can prove that this is indeed a Lipschitz operator seminorm when I define it on n-by-n matrices in this fashion. Okay. What is the upshot of looking at Lipschitz operator seminorms? If you remember, I'm interested in minimal tensor products of operator system, or in particular, unital C-star algebras. So if in general I have two concrete operator systems here, X and Y, I can form their minimal tensor product. How do I do it? I represent the algebraic tensor product on the Hilbert space tensor product of H and G, and then I take the closure and operator norm. This is the minimal tensor product of my two operator systems, concrete operator systems. Now I want to define a Lipschitz operator seminorm on this minimal tensor product, given that I have a Lipschitz operator seminorm on the first of these two operator systems. So I want to define something like L tensor 1 on this minimal tensor product. Okay, I want it to be a Lipschitz operator seminorm, so I should define it in each degree. So I look at n by n matrices with entries in this minimal tensor product. And so given such an n by n matrix of operators, I have to define the value of L tensor 1 to this matrix. Okay, how can I do it? I look at a finite rank projection Q on the second of these Hilbert spaces, and then I cut down set by one tensor Q from both sides. When I do that, I can identify this operator here with a matrix of operators with entries in X, operator system X. The size of this matrix is the original n from up here times the dimension of the image of Q. So I can identify it upon choosing an off-normal basis for the image of Q here. Then I get this identification. And then I can apply, I have my Lipschitz operator seminorm, it's defined in each degree, so I can apply it to this n by n matrix of operators in X. Then I take the supremum over all such finite rank projections. I have the value of L tensor 1 at this matrix set of operators inside the minimal tensor product. And it can be proved that L tensor 1 is again a Lipschitz operator seminorm on this minimal tensor product. And I can reverse the role of X and Y if I want to. So if I start out with a Lipschitz operator seminorm on Y, call it K, I can construct something like one tensor K using similar construction, of course. Okay. I wanted to talk about what is a completely bounded compact quantum metric space. And I'm going to use my characterization of compact quantum metric spaces in terms of finite dimensional approximations in order to find this completely bounded notion. So let's see. So I have to define what is a completely bounded finite dimensional approximation of a pair consisting of an operator system and a Lipschitz operator seminorm. So I'm going to take my previous definition and then I put completely bounded everywhere. That's how you do it. That's the only way to generalize to a completely bounded setting. So let's see what it says. So this is also a good reminder for the previous definition. It's repeated here just with completely bounded instead of bounded. So a completely bounded approximation, again, you have your two constants, epsilon and c. So it's an epsilon comma c approximation of this pair. X is an operator system, L is a Lipschitz operator seminorm. Okay, it's going to be two unital linear maps taking values in an auxiliary operator system set. Same as before. But now I have my inequalities just as before, but they should hold not just for operators inside X, but for all matrices of operators in X. So what are they saying now, these inequalities? It says that iota here is completely bounded, and the inverse of iota is also completely bounded. I have an upper bound on the completely bounded norm. That's my constant c. Phi is also completely bounded. C is an upper bound on the completely bounded norm. As before, image of phi is finite dimensional, nothing changes. And 3, iota and phi should be close to one another. So this is the completely bounded approximation part. Iota is close to phi when compared with the Lipschitz operator seminorm. So I have the same inequality as before, but it should hold for all n by n matrices with entries in X. So here it's important that I can apply my seminorm to a matrix of operators inside X in some controlled fashion, which is what I'm saying when I say I have a Lipschitz operator seminorm. This is a completely bounded finite dimensional approximation, and now comes definition of a completely bounded compact quantum metric space. Okay, so now I have a Lipschitz operator seminorm, and then I say that the pair consisting of this operator system and my Lipschitz operator seminorm is a completely bounded compact quantum metric space. It's almost the same as my previous two conditions that gave me my equivalent characterization without the completely bounded, outside the completely bounded setting. But the first inequality, which said that I could dominate the quotient norm by the Lipschitz seminorm, is slightly different now, because I have to mod out by not just scalars. I have to mod out by n matrices with scalar entries. Why do I have to do that? It's because my Lipschitz operator seminorm will automatically vanish on n scalar matrices. So I have to mod out by something larger over here in order to ever get such an inequality. And again, it has to hold for all matrices of operators inside X. Second condition, I need to have a completely bounded epsilon comma c approximation of my pair, and I should have one for all epsilon strictly greater than 0. Again, my constant c is global, so it's not allowed to depend on the epsilon. Okay, you can ask now, Jens, do you have examples of completely bounded compact quantum metric spaces, or are you now developing an empty theory? And there's a very good class of examples here, which is, I think that those are the motivating examples for Riefel when he started looking at compact quantum metric spaces. So this concerns ergodic actions on compact groups. So if you have a compact group acting ergodically and unitally on a C-star algebra A, ergodically on a unital C-star algebra A, so you have a strongly continuous action, the fixed point algebra is just the scalars. And you also have a length function on this compact group. And then I can also define one of these Lipschitz operator seminorms. My operator system is just the unital C-star algebra A. So I have to define what my Lipschitz operator seminorm does to an n matrix with entries in A. Okay, what do? I take something like the norm of the derivative at the unit. So I look at a supremum over all elements in my group except for the unit. And I take the supremum of the distance between action of G on X minus X divided by the length of G, which is the distance from G to the unit. And this is my seminorm in each degree. You can prove that this collection is in fact a Lipschitz operator seminorm, and that the pair consisting of this unital C-star algebra and this Lipschitz operator seminorm is a completely bounded compact quantum metric space. So I have done very little when proving this proposition. I just went through Riefel's argument and checked that it actually carries through to a completely bounded context. There's not much to do here, but it's quite nice that this is the case. So I think we are ready for the main theorems. Okay, so suppose now that I have two completely bounded compact quantum metric spaces, x comma L and y comma K. I can then look at their minimal tensor product, this operator system here, and I can equip it with a Lipschitz operator seminorm, which is just the max of L tensor 1 and 1 tensor K, which I showed you previously how to construct. And I can prove that this pair here is again a completely bounded compact quantum metric space. So if you work with completely bounded compact quantum metric spaces, the theory is compatible with taking minimal tensor products. That's the main message for this talk. It has applications to spectral triples, spectral metric spaces comes here. So if you have what is a completely bounded compact spectral metric space, that's an even unital spectral triple, such that the pair consisting of the unital C star algebra A, considered now as an operator system, and this Lipschitz operator seminorm coming from my unbounded self-adjoint operator D, when this pair here is a completely bounded compact quantum metric space. And you have a completely bounded spectral metric space. And you can prove that suppose you have two completely bounded spectral metric spaces, then you can look at the exterior product using this unbounded product operator as a minimal tensor product of the unital C star algebras, this Hilbert space tensor product. This is again a completely bounded spectral metric space. But I don't know how to prove such a result if I don't work with completely bounded spectral metric spaces, if I just work with spectral metric spaces. I should also say that I don't know any good examples of spectral metric spaces that are not completely bounded spectral metric spaces. So it's a challenge to find one. And I think this was everything I wanted to say. So yeah, I can finish early. So thank you very much for listening.
Thanks, Jens. Other questions?
So I have a couple of questions. I don't know how to raise my hand with the Zoom, sorry.
Oh, it's okay. Just...
So actually my questions, basically you answered is related to last two comments. So you say that you don't have good examples of spectral metric spaces that are not completely bounded, but do you have examples, even not good?
Yeah. So actually, the example I gave in the beginning, if you have a compact spin manifold, and you look at the spectral triple you get from this compact spin manifold, let's say you're in the even dimensional case, this is a completely bounded spectral metric space. Yeah, and yeah.
No, my question was an example which is not completely bounded.
Yeah, so I don't have any such example of a spectral metric space which is not completely bounded. This is a challenge to find one, I think.
But you believe that not every one is completely bounded, let's say.
Yeah, that would be a surprise.
But even without spectral triples, if you just look at quantum metric spaces.
Yeah, but there, I mean, so the thing is that if you have a spectral triple, you have a canonical way of defining a Lipschitz operator seminorm. I mean, you have a canonical way of defining a seminorm also on n by n matrices. So, I mean, whether you have a completely bounded compact quantum metric space or not, it depends on how you define your Lipschitz operator seminorm on n by n matrices. But again, I don't have good examples of.
And so my other question is similar. So you say for spectral metric spaces without the completely bounded condition, so it is an open problem to understand if the product of is still a compact quantum metric space, let's say, is still a spectral.
Yes, this is an open problem.
Okay.
But yeah, one should probably look for a spectral metric space which is not completely bounded.
Okay.
Is the first stage. Then you have some hope, right? Yeah.
Okay, thanks.
Yeah.
Other questions? I have several, so I can easily fill the rest of the time, but I won't insist because I'm the organizer. But maybe one is, kind of opposite to what you did was to not make it matricial at the level of the norms, but at the level of the states.
Oh, yeah.
Which was done by David Kerr. So you're aware of this work, right?
Yeah. I don't see any immediate relationship.
No, you cannot transfer one to the other by the usual
I don't think so. I mean, so the thing is that that what happens here. So I haven't worked on this for super long time, but what happens here is that you can actually. So once you have a state on your operator system, it also extends if you apply it interwise to n by n matrices. You get values in n by n scalar matrices. It's a conditional expectation. And so but then you get a different metric on the stage for each n once you have a completely bounded compact quantum metric space. So I think it's quite interesting to try to understand how these different metrics depend on the size of the matrix. I think this is quite relevant.
Yeah, sure.
Yeah.
And one other thing is you call it completely bounded. So why do you call it completely bounded if you work in the context of operator systems? I mean, completely bounded refers to operator spaces typically. So why do you call it like this? Just out of curiosity.
Okay, but so I mean, if you have an operator system, it is in particular an operator space.
After some work, right?
Yeah, but I mean, the way I defined it now as a concrete operator system, it's already sitting as bounded operators in a Hilbert space.
On the other hand, you do emphasize the fact that it's an operator system, so you have the matrix order.
Yeah, right? Yeah, sure. But this is, yeah.
But okay,
yeah, but
maybe we should discuss this.
Yeah, I think so. Yeah, so there's an abstract characterization also what it means to be an operator system.
But that's the one you're referring to when you use the matrix structure, the matrix order. Because otherwise you could just work with the operators, right? If it's concrete and but it's important to keep this additional structure into account, the matrix order.
You constantly know what happens on a matrices indeed.
Precisely, yeah.
This is the point of the whole talk. Yeah, yeah. That's one of the. Let's go back. So here, operator system is concrete for me, but I am keeping track. So in particular, X is an operator space. It's an operator space with extra structuring that you have a unit and you have an adjoint.
Sure.
Yeah.
Okay. Any other questions?
What about the assumption even? Do you use even?
Yeah. I'm not using that. It's just because I don't want to go through all 4 cases of the exterior product.
Okay.
That the particular product operator depends on the parity that you're working with. So I just fixed even for this talk, but in general you can deal with all of them.
Okay.
Yeah.
But you can transform in any case any spectral triple in an even one with the same metric on state space. I mean, the standard tensoring with the Pauli matrices doesn't change the metric, right?
No, but that would make it trivial, I guess, from a homology point of view. I mean, yeah. I mean, you could change so you work with graded C-star algebras instead, but that's kind of messy for constructing L tensor 1 or 1 tensor K. Yeah. But sure, I mean, I could pass to even spectral triples in general, but I think it's, I mean, from point of view of homology, that's not a very nice thing to do. Yeah.
Yeah, but okay. I mean, when you take the product of spectral triple, that is what you do. If you have 2 odd spectral triples, basically you turn one into even, and then you take the standard product. You add these tensors Pauli matrices. So basically,
yeah. That is, that is.
I don't know
true.
if that is trivial from cohomology point of view, but okay.
I mean, if you just stabilize by putting an unbounded self-adjoint operator on the antidiagonal, so that you have D equal to its adjoint sitting in the other corner, then this is trivial in cohomology. Yeah, that was what I was saying. But
all right, if there's nothing else, then we thank Jens again. Thanks a lot. And to all of us, see you next week. Thanks. Bye-bye.
Bye. Bye-bye.